Okay, so any questions? Just a reminder, the midterm will be Saturday. Sorry. April 1st, we will start at 13:30. We will be in P421, in this room, basically. Yes, your question. Well, it depends. If you want to postpone it and if you agree on a different date, then that's fine with me. Postpone it for a week, for example. But I mean, you should first agree on a date. We should all agree. And if you postpone it, of course, any topic that we will cover will be included in the midterm. Other questions? If you remember, we were discussing the Heisenberg picture. And the difference of in Schrödinger picture, we had these states. Let's say if initially we started with a state alpha t0, of course the state will change in time, that's what we expect. In fact, what we observe is that the observables are changing in time. So, and we can describe this change either because the state is changing, that is the approach we have in the Schrödinger picture, so we define this operator U, which evolves our state from t0 up to t, and this is our state alpha t0, t. This is our Schrödinger picture. Where the operators do not depend on time unless they have an explicit time dependence. And in the Heisenberg picture, what we do is just first noting that it's the observables or averages that are changing in time. So basically, these are what should be changing in time. If we have an observable A, this should have some time dependence. Now, in the Schrödinger picture, the time dependence is due to the fact that this bra and the cats, they are changing in time. But we can basically say the same thing by writing this as alpha t0, our initial cat, initial bra, U dagger, A, U, and the final bra. And this is what we call the time-dependent operator in the Heisenberg picture. Let's say, if you want to make it explicit, this is the Schrödinger picture, observe operator, and H is the Heisenberg picture operator, which depends on time, which changes in time. In the Heisenberg picture, it's not the cats describing the states that are changing in time, it's the operators that are changing in time. And then we had looked for the time dependence of how these operators change. We looked at the time derivative of this operator, assuming that it doesn't have any explicit time dependence, so the only time dependence is due to the Hamiltonian of my system. And it turned out that this is equal to 1 over I h bar AH. So this is in the Heisenberg picture, in the Heisenberg picture. And then we went ahead and made an example, made the exercise that we looked at when h is equal to p squared over 2m plus some v of x. And dx by dt, we just calculated this commutator. And just as in the classical physics, this was just p over m, the velocity operator. So basically, the one advantage of this Heisenberg picture is that the classical equations of motions are already over there. So we know that in quantum physics, classical physics is contained in quantum physics to an extent. Now, any questions?
Şuradaki equation özü biz state'i sıfırdan sonrasında şey yapabiliyoruz ya, anlayabiliyoruz ya. Biz geçmişini öğrenebiliyoruz peki o şey. State değişiyor zaman. Yani bir şey. Şimdi geçmişine de bir veri alabiliyoruz.
Well, in principle, yes. I mean, you see, here if you look at this definition, we don't really assume that t is after t0. We assume that t is some arbitrary other time. But there's one thing you have to pay attention to, is the measurement. How do you create your initial state? How do you know what your initial state is? You basically make a measurement. For example, we had looked at the case of the Stern-Gerlach experiment. To create a state in the plus state, we just send our initial beam through a Stern-Gerlach apparatus, and we just picked up only one of the beams. Now, you cannot reverse this. So once you cause the wave function to collapse, collapse is not reversible. Time evolution is reversible. So that's kind of one of the things that people don't like about the Copenhagen interpretation. There's something that is not reversible there.
Hocam iki farklı gözlemcinin yaptığı ölçümde birbiriyle uyumlanmak zorunda mı?
What do you mean by two different observables making the
Ben bir
measurement?
şey ölçtüm diyelim ki başka bir arkadaşım başka bir şey ölçtü. Daha doğrusu ben bir şey ölçtüm. O ölçtüğüm şeyi daha sonra başka birisi ölçtü. İkisi tutarlı olmak zorunda mı?
It's on the same system.
Evet.
So what you are saying is you have your system, you make measurement 1 at the time t, and find, let's say, A1. And then there is measurement 2 at time t, t2. This is at T1, at T2, and you measure A2. So are you asking whether A2 is equal to A1? Well, it depends. If the observable A does not evolve in time, then they should be. Or that if it is conserved, they should be the same. If it's not conserved, then they can differ by the difference of T2 and T1.
Yani birincisi ölçüm yaptığı zaman dalga fonksiyonu neye çöktüyse, ikincisi de ölçüm yaptığı zaman aynı şeyi bulmak zorunda.
If T2 is right after T1, yes. But that is in the limit. T2 goes to T1, A2 should be equal to A1. That's what we call the compatible observation. This is not compatible observation. This is the, for a measurement to have any sense, this is what we expect.
Bu olay aynı zamanda operatörün artık Heisenberg picture'dan bakıyorsak operatörün öbür türlü cat'in time dependence'ına da bağlı olacaktır o zaman.
You see, measurements are independent of which picture you use to describe your system. They should be, and they are because of this equality over here. You see, whether you look in the Schrödinger picture or in the Heisenberg picture, if you are doing a consistent job, then the expectation values do not change. So basically, observations, measurements are about your physical system, about the real world, in a sense. Our picture is just our mathematical formalism. Now, there's just one subtle point that you have to make, you have to pay attention to in this Heisenberg picture. You see, we said that the cats do not change in time in the Heisenberg picture. But keep in mind that these are the cats describing my system. Those do not change in time in the Heisenberg picture. Now, what about the base cats? So they're not really cats describing a system. So let's look at the base kits. Now, first of all, how do we choose the base kits? Well, there are many ways to choose the base case. It's completely arbitrary as long as they are orthonormal and complete. But most of the time, how do we choose base cases? Yeah, we just pick up any observable and look at the eigenstates. They don't have to be compatible. We don't need to consider two observables. It's enough that we have one observable, there will be a Hermitian operator corresponding to that, and it will have a set of eigenkets. And those eigenkets, we properly normalize them, we properly orthonormalize them if they are degenerate, and then they form our base cats. So this is our observable A. At least in the Schrödinger picture, we said that, okay, let's assume that A acting on these kets are the eigenvalue multiplied by the kets. So, and AI, AJ, we can choose them to be orthonormal. Well, if there is no degeneracy, then this is automatic. If there is some degeneracy, in that case, we have to do some more work. But in either case, we can choose an orthonormal basis corresponding to eigenkets. Now, the problem is, you see, we had already seen an example where in the Heisenberg picture, our operator at some time, and the same operator at some other time is non-zero. It doesn't have to be zero. It can be zero for certain operators, but it doesn't have to be zero. Now then there is this problem. So will we insist that our eigenkets are eigenkets of my operator A at the time t at all times? Or will I just choose my base cats as the eigenkets of my operator A at a given time? Now the issue is, let's take well, you are just free to do whatever you want. You can choose both of them. You can choose your base case as the eigenkets of your operator at a particular time, or you can also choose your base case as the eigenkets of the operator A at all times. So let's see, we already know that AS acting on AI is AI. Now let me do a trick. Let me put U dagger over here, and U dagger, U over here. This still holds. So because U dagger is 1. Let me multiply both sides by U dagger from the left. Now let's see, this is 1. This is my operator in the Heisenberg picture, let's say at the time t. So my operator in the Heisenberg picture at the time t, acting on U dagger, let me put the time in this time labels, tt0 AI. This is equal to AI U dagger tt0 AI. Now you see that the eigenket of the Heisenberg operator is not AI at all times, but it is this one, AI. Let me put the label t also. U dagger tt0 AI. These are the eigenkets of my operator. You see, the eigenvalues do not change. They have the same eigenvalue. Now, that is also something we expect, because you see, the Heisenberg operator at any time is related to the Heisenberg operator at any arbitrary time by a unitary transformation. So the Heisenberg operators at different times are unitarily equivalent. So we had already seen that unitarily equivalent operators, they have the same spectrum. So eigenvalues do not change. But the eigenkets, they change in time. And you see, in the Schrödinger picture, the state kets, they evolve by U. In the Heisenberg picture, the base kets evolve by U dagger. So let me give an example to this one. Now these are my base kits. Let's just take the case that my base kits need not be unitary. I can rotate them. Let's just assume that they are rotating with angular frequency omega. It's the base kits that are rotating. This is my state kit. Let's say V, my vector V. It has an X component. It has a Y component. Now this time, my state kit does not change. It is fixed in the Heisenberg picture. So my state kit is fixed, but my basis coordinates are rotating. So this V at some point can be in the direction of X, at some point can be in the direction of Y, etc. So you see that the components are time dependent now. Vx of t, Vy of t. Well, let's look at if the same thing happens in the quantum picture, in the quantum mechanics. Let's say we have an arbitrary operator, arbitrary ket, initial ket. This is equal to, we had seen that this we can write as Ci AI. Now this Ci is given by AI alpha. This is in Schrödinger picture. Let's say. Now, so Ci of t in Schrödinger picture still, those coefficients will be time dependent. It will be AI alpha of t, which is AI U of tt0 alpha, which we can also write as U dagger tt0 AI dagger inner product with alpha. But you see, this is nothing but AI of t alpha. Now we make the transition to the Heisenberg picture. You see, in the Heisenberg picture, my ket alpha is nothing but Ci of t AI of t. In the Heisenberg picture, the base kets depend on time. This is our Heisenberg picture. Alpha of t is equal to Ci of t AI. This is the Schrödinger picture. Well, in the Schrödinger picture, the operators are independent of time, so their eigenkets are independent of time. They make a time-independent basis. The state ket is time-dependent, alpha of t, and that is called by the time dependence of the coefficients. Okay, back to this example. The Schrödinger picture is like keep the axis fixed and rotate your vector v in time. That is our Schrödinger picture. What happens in the Heisenberg picture is the base kets are time dependent. These alpha I, AI, T's are time dependent, but in a sense they are rotating in the opposite direction because they are evolving by U dagger, not by U. Ci of T is also time dependent. The coefficients are time dependent. Well, just like look at this example. V is, if you want to keep V fixed, although the coordinates are rotating, you have to make sure that the coefficients, the components are time dependent. So that is what we have over here. The base kets are time dependent. The coefficients are time dependent, but they are time dependent in such a way that the time dependence of the base ket cancels the time dependence of the coefficients. So the resultant ket, state ket alpha is independent of time. So it can be kind of misleading to say that in the Heisenberg picture, all the kets are independent of time, depending on how which ket you are talking about. The ket describing the state of your system will be independent of time in the Heisenberg picture. But the kets that corresponds to the eigenkets of your operators will depend on time. Basically, your operators are changing in time, so it should be eigenkets. What is evolving? That is the whole idea about between these two pictures. What we see is observables are evolving in time. So if I just drop an object, you know its position is changing in time. That is your observation. Your observation is not the ket. You are not observing the ket. You are observing the observables. And basically, in quantum mechanics, we have two different ways of describing this change. Either we say that the operator corresponding to the observable is changing with time, or the ket describing the system is changing in time. They are equivalent. They are the same picture. They give the same result. It's just a different way of looking at it. It's exactly the same thing. It's just like choosing some coordinate axis. You see, let's see, if you are studying, I don't know, the trajectory of an object in the close to Earth, you would probably prefer to choose a coordinate axis in which Z is in the direction of G, right? I mean, you don't have to choose it, but making that choice will simplify your life. The same thing appears over here. So you don't have to choose a Schrödinger picture, or you don't have to choose the Heisenberg picture, but certain things are easier to prove in one picture and certain things are easier to prove in the other picture. So one question is, for example, what about the classical equations of motion? What do they correspond to? Well, in this Heisenberg picture, it's just clear that they expect the operators themselves satisfy exactly the same equations of motion as their classical analogs. Well, you can do the same thing also in Schrödinger picture in terms of the expectation values. But basically, it will just make your life a bit more complicated. You are just free to use whichever one you like. They should both give the same result if you do everything properly. In observables, sorry. They should give the same result about the observables. If they don't, then you are doing something wrong. Let's do another example of this time evolution of operators. Let's look at the harmonic oscillator. The Hamiltonian we have is p squared over 2m plus 1 over 2m omega squared x squared. This is one-dimensional harmonic oscillator. What is the x by dt? In the Heisenberg picture. How do you derive it? Well, we had already done a similar example. This was pi over m. What about dp by dt? Why do you think it is 0 in this problem? Well, it is still 1 over IH bar, P of H. And if you calculate it, it just turns out to be minus del over del x of 1 over 2 m omega squared x squared. So the dp by dt is just minus m omega squared x. So if you take the second derivative of x with respect to t, the first equation just tells us that this is 1 over m dp by dt. And if you use the second equation, this is just minus omega squared x. So d squared x by dt squared, this is nothing but minus omega squared x. And if you try to solve this equation, you will see that x of t is equal to a cosine omega t plus b sine omega t. Now, what are a and b? Well, let me also calculate p of t. You see, p of t is nothing but m times dx by dt. So if you just take the derivative of x, this is m minus m omega a cosine omega t plus mb sine omega t. Now x of 0, x at t equal to 0 is just x0. This is a. Now p of at t equal to 0, this is p0. This is just minus this is sine, this is cosine, plus mb. So we know that a is equal to x0, b is equal to p over m, p0 over m. So we know x of t is equal to x of 0 cosine omega t plus p of 0 over m times sine omega t. And p of t is equal to minus m omega x0 sine omega t plus p0 cosine omega t. So if you want to calculate how the expectation value of x changes as a function of time for any state alpha, this is nothing but its value at t equal to 0 times cosine omega t plus the expectation value of p in that state times sine omega t over m. Now, classically speaking, for example, if you have a harmonic oscillator, one typical example will be you have a spring, you just extend your object by some distance. That is the average of x for your object at t equal to 0 will be some distance, let's say d. And you just release it from rest. Well, that would just mean that P0 at alpha t equal to 0 will be just 0. So in this state, x alpha of t will be just d times cosine omega t. Now this is nothing but the classical solution. I don't even know what this state alpha is. It's just its average at t equal to 0 should be some d.
Şöyle bir şey unuttuk. Birim hatası var da.
Where?
Siz ve tek kelime.
Beynin yanında bir x daha almış.
Here I have an omega, here I have an omega, so it is m omega. Well, you see, you can prove the same thing for a particular ket in the Schrödinger picture, if you want. Because the expectation values in the Schrödinger picture and in the Heisenberg picture, they do not really change. But here, well, you can also prove it for a general ket in the Schrödinger picture. But it will not be as easy. Any questions? Well, let's continue with the harmonic oscillator. Well, it's one of the most fundamental problems we have in physics. Basically, it's one of the few problems where we can actually solve. And well, there are many other problems we can solve, but they are not really relevant for physical applications most of the time. Now, the reason why the harmonic oscillator is so fundamental is that just look at any potential for an arbitrary system. We know that the potential has to be a minimum. Physics always likes to move to the minimum of the potential. It can have some arbitrary shape. Well, physics, if you leave it on its own, it will dissipate energy in the system, and it will eventually settle close to the minimum of the potential. So somewhere over there. But close to there, my potential overlaps with this function, this parabola. So let's say this is some coordinate x. U of x will be around that minimum point, u of x0 plus du by dx evaluated at x0 times x minus x0 plus d squared u by dx squared x minus x0 squared over 2 plus etc. Well, this is just a constant which we can just choose to be 0. I mean, you can just choose your potential, shift your potential energy by any constant you like. I can just shift it such that that becomes 0. In the minimum, this is 0. Since x0 is an extremum. And the second derivative of u is, this is larger than 0. Since x is equal to x0 is a minimum. So you see, sufficiently close to the minimum, and any system will try to go to the minimum, sufficiently close to the system, our system just behaves like an harmonic oscillator with a potential that is quadratic in its deviation from the minimum. So this system can be anything. It doesn't have to be a single particle attached with a spring. I don't know, if you have solids, you can just describe the motion of a single atom by this model. You can even get a good enough description for the electrons in any solid. So as a starting point, this is our starting point for most of the problems that we study. We first approximate it with a harmonic oscillator, and then we add the corrections to it. So let's study what the harmonic oscillator will tell us. This one, the square. Well, I can also choose my origin such that x0 is 0. So if I choose x0 is equal to 0, h will be equal to p squared over 2m plus 1 over 2 kx squared. So this is what we call k, the second derivative of the potential at the minimum. Now, first of all, let's look at x squared, and let's consider it any ket. Well, in the coordinate space, we can write this as an integral of psi x star, x squared psi x, which is nothing but dx, x times psi x star, times x times psi x. But you see, the integrand is positive all the time. So x average of x squared in any ket is always 0, is always larger than 0. Well, similarly, you can just show that p squared in any ket, its average is always 0. So they are definitely positive operators. But this means that the h in any ket alpha is always larger than 0. Well, I don't know. It can be larger than or equal. But you see, if it is to be equal, the wave function has to be exactly equal to 0. So equality sign, I won't really have it. Unless psi is 0, there's no equality sign. So neither here. Average of h cannot be equal to 0. Now let's just choose alpha to be an energy eigenkette. So h acting on alpha is equal to E alpha. But if this is the case, then the average of h in this ket is nothing but E alpha, which should be definitely larger than 0. Okay, we didn't do much yet, we didn't achieve much yet, but at least we know that the spectrum is bounded from below. The energy eigenvalues, all of them has to be positive. And they cannot even be 0. So the ground state energy, the minimum energy state is definitely positive. Now let's try to play with it. H is equal to p squared over 2m minus 1 over 2mx squared, no, plus. Well, if it was a minus, it would have been nice, because in that case I would have a difference of 2 squares. I can factorize it. Well, I mean, we are just playing it for the time being. Well, if it's a plus, but still I can make it the difference of 2 squares. Let me write it in this form. Square root of m over 2x squared minus pi times p over square root of 2m squared. Well, I squared brings me another minus sign. Well, that also looks nice. So h seems to be equal to this one. minus I p over square root of 2m square root of m over 2x plus I p over square root of 2m. Well, it looks nice. So we have just the product of two things. I'm not putting an equality sign because you see, if you just take that square, if you just calculate that square, this gives you m over 2x squared. Sorry, I have an omega over here. M omega squared. Well, the product of the first terms is this one. Product of the second terms is 1 over 2mp squared. Well, this is my Hamiltonian, but I have additional terms. I have the first and the first and the second term, which gives me a square root of m over 2 omega times I over square root of 2 omega xp. And the product of the second term and the first term gives me minus I over square root of 2m square root of m over 2 omega px. The first two terms is nothing but the Hamiltonian I want. H, but I have these additional terms. Let me simplify it a bit. So I have the I omega over 2, which is common in both factors, xp minus px. Well, if these were just classical numbers, then this would have been just 0. So my factorization would have been perfect. But since they are operators, the factorization doesn't really work that way. So we have to correct by this factor. What is this factor? Pi h bar? I h bar minus I h bar? So this is nothing but xp. This is I h bar. So this is equal to h minus h bar omega over 2. So you see, now we have this additional term. So this is Hamiltonian is equal to this product plus h bar omega over 2. You see, I factorized it, you are right, but factorization assumes that those factors are commuting. You see, if x and p were commuting, this xp minus px would have been just 0. They are not equal because they are not just ordinary numbers. They are operators that do not commute. So that's why factorization doesn't really work the way that it works in just ordinary numbers. So that's why I didn't put the equality sign over here. Just to make sure that they are equal, I just multiplied out the parentheses, and it turned out to be not to be equal. Well, it's not really a big deal because it's just a constant. That constant I could have just shifted my potential to set that constant to be to 0. You see, I already assumed that u of x0 is 0 in this expansion. But if I had chosen u of x0 to be minus h bar omega over 2, then that would have canceled this h bar omega over 2. So that's not really a big deal. So you have to be a bit careful about the things that you know about ordinary numbers and applying them to operators. Now let me call this one A, whatever that operator is. Is it a Hermitian operator? No. X is a Hermitian operator, P is a Hermitian operator. If you take such a superposition, due to the I over there, a dagger is not equal to itself. But this is a dagger. Whatever that operator A is, the parenthesis on the left is its dagger. Now let's look at the properties of these new operators that we define. I mean, for us, one of the most important property of operators is their commutator. Do they commute with each other? Do they anti-commute? Let's look at the commutator. A dagger A. This is equal to square root of m over 2 omega x minus I p over square root of 2m and square root of m over 2 omega x plus I p over square root of 2m. Well, the commutator of the first terms is 0. It's just x commutator with x. The commutator of the second terms is 0. It's the commutator of p with p. So it's the commutator of the first and the second term, and the second and the first term that will be non-zero. So this is equal to square root of m over 2 omega x I p over square root of 2m plus minus I p over square root of 2m m over 2 omega x. Well, these numbers, I can just take them out of the commutators. So this will be equal to I omega over 2 commutator of x and p plus or minus I omega over 2 commutator of p and x. But this is nothing but I omega commutator of x and p. Because in the second term, if I just change the places of p and x, that gives me another minus sign. It makes that relative minus sign a plus. So the first term and the second term, they are basically equal to each other. And what is the commutator of x and p? IH bar or minus IH bar? IH bar minus, so this is IH bar minus h bar omega. Well, conventionally, let me just change the names. Let me call this B. Well, conventionally, for reasons which will be apparent in a moment, we usually want these defined new operators whose commutator is plus or minus 1. So I just define A to be B over square root of h bar omega. And similarly, a dagger would be just B dagger over square root of h bar omega. So a dagger A is just minus h bar omega, minus 1. And now my Hamiltonian, in terms of these operators, is nothing but h bar omega, a dagger A, plus h bar omega over 2. This is my Hamiltonian operator. Well, I have three operators in my hand. I have the A, I have the A dagger, I have the H. I have already studied the commutator of A and A dagger. What about H? Let's see what the commutators of H and A dagger are. Let's look at H and A. H bar omega, A dagger A plus H bar omega over 2, A. This is equal to H bar omega, A dagger A, because A commutes with H bar omega over 2. Well, here H bar omega is a constant. I can just take it out. What remains on the left, I have the product of two operators. In the commutator, I can expand it. So this will be A dagger, commutator of A and A, plus A dagger commutator with A times A. I'm just using the property of the commutators, that the commutator of A, B with C is A, B, C plus B, no, plus commutator of A and C, B. Just keep in mind that A, B, C, their order should stay the same. A, B, C order is fixed. No, not A, B order is fixed. So that's why in the second term, the B is on the right of the commutator. HA is equal to H bar omega. Well, you see, every operator commutes with itself. A commutator with A is 0. Well, the second operator, we had already calculated it. The commutator of A dagger and A is -1. So minus A. So this is minus H bar omega A. HA is equal to minus H bar omega A. Now this will be interesting. You see, you have one operator that commutes with the Hamiltonian. Now that doesn't commute with the Hamiltonian, but the commutator is some constant times itself. So whenever you see such an operator, we will see what it implies for the spectrum. Well, I can do the same thing for a dagger, but rather than just calculating the commutator, let me take the dagger of this thing. HA dagger is equal to minus H bar omega A dagger. Well, HA dagger is nothing but a dagger commutator with H. This is equal to minus H bar omega A dagger. Or H commutator with A dagger is equal to H bar omega A dagger. So A dagger is also such an operator. Its commutator with the Hamiltonian is proportional to itself. Now let's see what these imply for the energy eigenkets. Let's look at this alpha, which is an energy eigenket of the Hamiltonian with energy eigenvalue E alpha. Now let me look the commutator of Hamiltonian with a dagger, with A. Let me act on the ket alpha. Now on one hand, I know that this is nothing but HA alpha minus AH alpha. This is the commutator. This is the definition of the commutator. But this is equal to HA alpha minus A E alpha alpha, since alpha is an energy eigenket, that is, we are studying an energy eigenket. This will be equal to H minus E alpha acting on A alpha. Now what I did was in the second term, E alpha, since it's just a number, it commutes with A. I just move it to the left. On the other hand, I know that the commutator of H with A is nothing but minus H bar omega A. This is the commutator. This is equal to H minus E alpha A alpha. But you see, that means that H acting on A alpha this should be equal to E alpha minus H bar omega. But this means that A acting on this ket alpha, which was an energy eigenket, is also an energy eigenket. It has a different energy. And its energy is lower than the energy of this ket alpha by H bar omega. So I can lower the energy of my kets by acting on them with A. But you see, I already know that the energy of any kit should be larger than 0. So I shouldn't be able to lower it indefinitely. Now, A of alpha is an eigenkit with a lower energy as long as it is not 0. So I can lower the energy of any kit by acting on with A. I get a different kit if not 0, which has a lower energy. But I know that the energy of my Hamiltonian is bounded from below. It cannot go, it cannot have smaller and smaller values. Somewhere this process should stop, should terminate. But the only way to terminate this process is if A of alpha is 0. Because if A of alpha is 0, then I cannot say that it's an energy eigenkit. It's nothing. Sure. Why not? It is annihilated by my operator. It's just consider, for example, the subtraction of a, okay, so let's see. Just consider the case in real space by multiplying by a number. That if I choose that number to be 0, whatever vector you give to your operator, if you multiply it with 0, it becomes the 0 vector. Here the Hamiltonian is not the 0 operator, but nevertheless on a particular kit, when I act on the Hamiltonian with this particular kit, it just gives me 0. Or just look at a system which has an eigenvalue that is 0, energy eigenvalue that is 0. If you act with the Hamiltonian on this kit, you get 0. Now let me give it a special name, A acting on 0. This is 0. This is my ground state. I know that there should be some ground state because the energy spectrum of the Hamiltonian is limited from below. It cannot go below 0. Now let us do the same thing for H A dagger. Now H A dagger acting on any alpha will be, on one hand it will be H A dagger acting on alpha minus A dagger H acting on alpha. Well, this will be H minus E alpha acting on A alpha. It's just A dagger alpha, sorry. The derivation is exactly the same as the previous case. Nothing really changed except that A becomes A dagger. Now the commutator of H and A dagger, we know that it is already H bar omega A dagger. Well, this just looks like the previous case with a change in sign. No, in the case of A, it was minus. Now, in the case of A dagger, it's plus. But this means that H acting on A dagger alpha is just E alpha plus H bar omega. A dagger acting on alpha. So you see, A lowered the energy. If I started with an energy eigenvector, acting with A on that energy eigenvector lowered the energy by H bar omega. Now A dagger basically does the opposite. If I start with an energy eigenkit, if I act with A dagger on this energy eigenkit, it increases the energy by H bar omega. Now I have my ground state. So my Hamiltonian acting on my ground state is Hamiltonian is A dagger A plus H bar omega over 2 acting on the ground state. But if I act with A on the ground state, it is just 0. That is how I defined it. So this is Hamiltonian acting on the ground state is H bar omega over 2. Okay, ground state doesn't have zero energy. Its energy is just h bar omega over 2. That is the minimum possible energy I can have. Let me define 1 to be a dagger acting on 0. I know that a dagger acting on an energy eigenket increases the energy by h bar omega. So this is 1 plus 1 over 2 h bar omega 1. Let me define n by a dagger acting n times. So h acting on this ket n, it is just, you see, every action of a dagger increases the energy by h bar omega. There are n of them, so it's just n plus 1 over 2 h bar omega. So this is the whole spectrum of the harmonic oscillator. Now, what about the expectation values of x and p? Those are the other operators we have. We can also calculate them. You see, here are my operators. This is my b. Divide by 1 over square root of h bar omega. This is my a. And my a dagger is 1 over square root of h bar omega, square root of m over 2 omega x minus I p over square root of 2m. Now let me see what is a plus a dagger. Well, if I just sum them up, the p terms, they will cancel. So I will end up having 2 over square root of h bar omega, square root of m over 2 omega x. The first terms add. So x is nothing but square root of h bar omega over 2m a plus a dagger. Omega is over here. H bar over 2m omega a plus a dagger. Now let me calculate this one. And you see, it's the state which has the energy n plus 1 over 2 h bar omega. Well, this is square root of h bar over 2m omega n a plus a dagger n. Now you see n a n. A lowers the energy by h bar omega. So when I act by A on the state n, I get the state n minus 1. But this is n, the state, the ket n and the ket n minus 1, they have different energy eigenvalues. We know that they're corresponding to different eigenvectors of the Hermitian operator, so they have to be orthogonal to each other. If you do the same thing for a dagger, this is proportional to n plus 1. It's again 0. Well, we didn't yet fix the proportionality constants, so that is something we have to study still. But basically the idea is the expectation value of x in the nth state will be 0. Now, if you want to calculate the non-zero matrix elements, for example, if you looked at the x squared matrix element of x squared, it will not be 0. But to be able to calculate that, we need to fix the proportionality constants. So basically, we had used that a n is equal to some number multiplying n minus 1, and a dagger acting on n will be probably some other number acting on n multiplying n plus 1. Now on Monday, we will see what is n and n prime. Now, any questions up to this point?
Yani expectation x'in sıkışmasına gibi zero yapacak minus alıyor. Bir de possibility kelimesini.
Well, and in a sense, yes, the energy eigenkets, we will also calculate the wave function. They are symmetric around x equal to 0. The probability that they will be at the positive value of x is the same as their probability at the negative value of x. So that's why the average of x turns out to be 0. Now, the classical systems, for example, if you have a mass, you would rather have some states that have non-zero expectation value of x. So when you make an observation of your of your oscillator, what you see is your mass is moving over there, then back, and its expectation value is changing with time. So first of all, it cannot be, and this also shows you that it cannot be energy eigenstate. That's not an energy eigenstate. That's a superposition of energy eigenstates. Only in that case you will have a non-zero expectation value of x. It will be changing with time, and we had already studied what that time dependence is. You see, we already know that for the harmonic oscillator, x of t is x of 0 cosine omega t plus p of 0 over m omega sine of omega t. This we already know. So there's no surprises over there. So we should start with a ket that has a non-zero expectation value of x. That is not an energy eigenket. That cannot be an energy eigenket. Then you can ask, well, in classical physics, that is a definite energy state, the one that is moving here and there. So what's the analog in quantum physics? How come in classical physics our observation that a particle localized at a given point is moving here and there is an energy eigenkit, whereas in quantum mechanics we say that it's not an energy eigenkit? So how can these two claims, let's say, be compatible? What is the classical limit, so to say? Okay, any questions? Okay, for midterm, if you want to change the date, I would advise you to, you don't have any lectures now, just stay here, decide on an alternative date, and let me know. If you all want to change. Otherwise, we will have the midterm this Saturday. Any questions? Okay, so see you on Saturday or Monday.